So just as a recap, we did start a discussion on what shear walls are and how they stiffen a building. We did look at this very simple consideration where we have an element in bending that is 200 by 200 and another one, same cross-sectional area, only that the dimensions are 100 by 400. And we saw that though the cross-sectional area is same, the second moment of area becomes significantly different just by changing the orientation. And from that, we say that just by elongating or changing the orientation of columns in a particular direction, we can change significantly the stiffness of a building in that direction. And then we went back to the column that we are working with in the hypothetical building. And we said, if we were to rearrange this column from 800 by 800 square to 200 by 200 rectangle section in plan, then that effectively will have changed that column into a wall. And we saw that by just doing that, the stiffness in that direction of that element could be increased by up to 16 times by just rearranging the dimensions. So I want us to continue from here today. Maybe I can make a discussion for a while, and then we can get some presentation from one or two other groups. Today is 26th. of October. This thing is misbehaving. 2023. 6th of October 2023. Now, so we could leave the columns square as we had put them earlier, and just decide to put some walls in some places. Just decide to put some walls on some base of the building, and effectively then those walls on some base of the building would then stiffen the building in that direction. Now, it is known that generally when you provide shear walls in a building, those walls have a tendency to carry almost 100% of the lateral load. It is known that when you provide shear walls in a building, those shear walls have a tendency to carry almost 100% of the lateral load in a building. I will write that as a note. It is known that when adequate shear walls are provided in a building, those shear walls tend to carry almost 100% of the lateral load of the building. Okay, so for example, the bell bottom next to our campus here, this cooperative building, those massive shear walls that are placed on the two ends of the building, when either wind or an earthquake is blowing or is pushing the building in that direction, those walls, for all intents and purposes, would carry about everything that is put into that building or into that structure in terms of lateral loads. This is a known fact. Okay. I'll make an attempt to justify this thought, though it might not be necessary for this level for you to grasp this particular concept. But what is important is that you need to know that it is true that when you have adequate shear walls in a building, then those walls tend to carry almost 100% of the lateral load that is put into that building. To try and discuss how shear wall carries the majority of the lateral load and not the columns several engineering facts are important to remember. One, strain cannot exist without stress. And vice versa. Okay, so maybe I've shared this thought with you before, but let me just remind us again. So we got a wall here. Put mass of the wall here. I push this wall, does it deform? I push the wall, does it deform? I'm listening. If I push
doesn't
the wall,
deform.
Mutero thinks it doesn't deform. If 10 of us push the wall, 10 of us, or 100 of us, let's make it more extreme. 100 of us push this wall. Does it deform?
Yes, it does. It's only that it's not visible, but because the stress is applied.
Correct. The wall actually does deform at the slightest force that you apply. I'll give you another example to make this thought clear. So we have small cars, like the Vitz. Then we have big vehicles, the trucks and the big buses. And we have a 50, I think it's a 52-seater bus, took on some buses like that. So when you board a small vehicle, you notice the deflection of the springs. When you board a bigger vehicle, like a bus, and you go onto a bus, one person, it's hardly noticeable. So why is it like that? It's because of the stiffness of the spring in relation to the amount of force. So the small vehicle has got a weaker spring. So when you as one person, 70 kilos, you board, that spring deforms appreciably. You can actually notice the deformation. When you board, you go onto the back of a truck. You know, I see sometimes on the road some guys hike a lift on trucks. So truck, they wait when the truck is maybe going onto an intersection, then they run and jump onto the truck. The spring doesn't show the deformation. Does it mean that it's not there? The truth is that that deformation is there. Back to the problem of the wall. If I push this wall, for sure it deforms. But because the stiffness of the wall is much bigger than the force that I'm applying, so the deformation is so small that you might not be able to appreciate it or to see it with your eyes. But that the deformation is there, courtesy of that small force. Yes, and if we put strain gauges here and we measured strains as I push this wall, we will actually be able to measure that deformation. Now, with that thought, whenever a lateral load is put onto a building, the building has to deform, even if it's a small lateral load, like a small gust of wind. So a small gust of wind blows this U block. Now there's wind since I came in early this morning. Is wind that is blowing from the side of the railways. It's blowing into the U block. Now that wind is really a small, tiny force compared to the stiffness of this building. Is the building deforming? The answer is yes. The building is deforming, only that the deformation is so small because the stiffness of the building is much bigger than the wind force that is causing that deformation. But you cannot have a stress that does not accompany is not accompanied by a strain. And if you see a structure or an element or a material deforming, straining, there must be a stress that is causing that strain. So that's the first truth that we have to be to remember when we want to think about why the shear wall carries 100% or almost 100% of the loading that is lateral applied to buildings. There's another truth. So, if we're agreeing on this one, then also the amount of deformation is directly proportional to the force and inversely proportional to the stiffness of the element. Inversely proportional to the stiffness of the element. So we've got in a building both shear walls and columns. So we have a building like the bell bottom is a good example, and it's next door here. It's got shear walls, or even the Times Tower. It's got a lot of shear walls outside. They are doing like this on the corners. So they're shear walls and they're columns, and they're tied together by the slabs. So if they're to deform, they will deform together by the same amount. You will not find that the column will deform more than the shear wall. Consistent deformations, if you can remember, because they're tied together, they have to deform together. If the shear wall moves a millimeter, so the columns also at that level have to move a millimeter. Consistent deformation. So if they are to deform together, and you apply a loading, for that loading to cause a deformation, it must deform both the column and the shear wall. If you're applying forces here, like you will do in the frame that you're trying to design, if you apply those forces, if this frame is to deform that way, that deformation has got to be of both the columns and the shear walls. But the shear walls are extremely stiff. And to these forces, the shear wall is like this wall to the force of my hand. So anything tied to this wall, if I was tied to this wall and you guys came to push this wall, and the wall refuses to deform, so I also don't deform. I also don't move with the wall. But the wall is a lot stiffer, so much stronger. This is the thought. We could dwell on it a little bit and say a bit more, but I think for your level it might not be very necessary to bash our minds too much to try and get that concept. However, as part of this exercise that you're doing, if you do it quickly, and we are able to get to a point where we have outputs before the end of the semester, we will do this theoretical exercise of shifting the shear walls and comparing the frame with this shear wall and this shear wall, like this. And it's very interesting and very good learning for you. And this kind of information, for those of you who will wind up as structural engineers, it will be very, very useful in your making decisions, engineering decisions. So your take home from these thoughts: generally, when a shear wall is provided adequately, it carries the bulk of the lateral load. And most, if not all, design standards advise the designer to load the full portion of the lateral load on the shear wall. So if you're designing, if you're doing a manual calculation, manual design check, manual analysis of a building that has got shear walls, you would load the rest of the vertical elements with gravity loads. So you will check the columns and beams to carry dead and live loads in the vertical, gravity loads. And then you take your calculated lateral load and you would put it onto the shear walls of the building, 100%. So you would analyze the shear wall for 100% of the loads, and I'll show you shortly how you would do that if you are doing this calculation manually. So you analyze the shear wall to carry the whole lateral load. You then design the shear wall to carry the whole lateral load from the resulting shear forces and bending moments. I've said most, if not all, design standards advise the designer to do this, because the shear wall relative to the other elements in the building is a much stiffer element. It's a much stiffer element compared to the vertical elements, the other vertical elements, basically columns in the building. So it makes sense to just load everything onto the shear wall. If you're designing by hand, if you're doing computer-aided designing, like what now we're trying to do as part of this coursework, as part of this course, is that you'll find that the software will use these two truths that we have. Mentioned here. The software to apportion the proportion of the lateral load that goes onto the shear walls and the portion of lateral loads that go into the columns. Just to give you an illustration. So what the software will do is it will do the stiffnesses of all these vertical elements, the shear walls and the columns. And then in that, once it does that, it will do a sum of those stiffnesses, and then it will distribute the lateral load in accordance to those stiffnesses. Yesterday, somebody asked me a question about the shape of the building and how that affects the earthquake forces in the building, and I gave some very general thoughts on it, but I mentioned two gentlemen. One fellow is called Muto and the other one is called Stodola. I think they were Eastern Europeans. They did a lot of foundational work in how even these stiffnesses are calculated and how the earthquake force would be distributed between the shear walls and the columns and everything. So if you're interested, you could look up work by these two fellows. I think they were professors, Professor Muto and Professor Stodola. Okay, and I did mention that I think our director, Professor Koteng, had the privilege of being a student to these people. Okay, in his when he was a young man, when he was doing his if you're interested, you can check up this. It's some bit of calculation, so it might not be very juicy, but there might be some few students who might be interested in this subject. You could actually dig up the works by these fellows and see how that distribution will be done. But generally, if you carry out those calculations, you find that the shear walls, like these two shear walls that we put here on this hypothetical building, will basically carry almost everything. So if you're doing hand calculations, you don't need to, bog yourself down with too much calculation at a time when you almost are sure that almost 100% of the loading will still, either way, will go into those shear walls. So it just makes sense to take this truth as it is, and to just load the shear walls with lateral loads, and then the rest of the vertical elements, that is columns, they will carry the gravity loads. So that's the take home I want you to bear in mind at this point. So now, with those thoughts, then how do we analyze the shear wall? How do we analyze the shear wall? So I write here, let's write it as a question, so that then so how do we, is the shear wall analyzed? I take you back to your second year, maybe first year, no, second year, when you did your analysis of structures 1 unit. There was a small topic before you went into the beams and the cables and the arches and the trusses. Before you went into those, there was a small subtopic called structural idealization. Idealization. So that's what we start with. That's where we start from, and we say that the shear wall is idealized is usually idealized as a vertical cantilever with bottom and the upper end free, and the upper end free. Basically, if I may draw this thing in 3D, it would look something like this. Sorry. So that's the wall. I've made an attempt to draw it in 3D. That's a shear wall. Sorry. The bottom is fixed. It's fixed. It's a fixed bottom. So we would say that's a fixed support. Fixed support. And then, if I may take you back to these forces that we calculated here. So if you can remember from the exercise you've been working on, that this column gives us the forces per floor. Okay, forces per floor. That Fx. Now that force, for example, if we calculated the force in the in the x direction, which is our x direction on this thing, is that way, x direction. So if we took, because we've drawn our shear walls to stiffen the y direction, so we'll pick the force in the y direction. Okay, remember we've put a shear wall here and the shear wall here. Okay, so we'll take the total force in the y direction, take the total force in the y direction, that total force, and we will divide it to the number of shear walls that we have in that direction. So, for example, on this example, on this sketch, I've drawn 2 shear walls here. So we take the force in the y direction and divide it by 2, so that each shear wall carries half that. It's a simplistic way of approaching it, but this is how we do in idealization, because it is when we're doing hand calculations, we want to simplify the problem as much as possible. If you can remember from that topic of idealization in your first structures unit, the reason why we idealize structures is so that we can make the structures so that we are able to make them to be able to be analyzed by hand. If we were to model them as they are in real life, it's next to impossible to get the correct to be able to analyze them. So then we would come and simply put the forces on that shear wall per every floor. So from first floor to 18th floor, we would come and just put the forces on that shear wall. We would do that. Forces, on the shear wall. Brian, if you could switch off your mic, you could mute your mic. Brian Toner. Brian, somebody tell him to. Somebody tell Brian to mute his mic. Okay. Okay. So that's how we would put in the loading. So it's every floor goes into a part of struggling this thing. Yeah, sorry. Just a moment. I'm trying to reorganize my. Okay. So this would constitute the first step in the analysis of the shear wall. We would idealize it as a vertical cantilever, meaning it is fixed at the bottom and it is free at the top. And then we would pull out the forces that we have calculated in that particular direction and divide those to the shear walls in that direction. And then we would apply those as point loads at the floor levels on the shear wall. So that would be the first step in how we would analyze shear wall. Of course, if we did that, then we would get an analysis output. So we get an analysis output, and that output will be that simply of a cantilever element loaded with point loads. We got a cantilever, we say the wall is a cantilever, fixed at the bottom and is free at the top. And then we will have discrete lines But generally they would follow something like that. But it won't be a smooth curve. Eh? It will be line segments. Maybe I should say that. Discrete PMD with discrete line segments and not a smooth curve. Okay, this again is just analysis of structures from your earlier units of analysis of structures. You got a cantilever with point loads, you get a discrete line of segments from there. This would constitute step number 2. And it will give us bending moments. Two things that you need to design for. One, you need to design for the maximum bending moment that the wall is able to take that. So if we extracted if we sketched this wall here, one of these walls, for example, we would have an element in plan that looks like this. Sketch that nicely. You got that wall that way. And of course we have this wall, as we said, we have its stiffness about that axis. That is what we're interested in. And we need to design the wall section for bending about this axis here, XX. Okay, and the moment that we are designing that wall section to carry is that maximum moment there. Okay, that is one of the design outputs that we need to do. Okay, and maybe we can, just so that we will remember that that would be a column that has been fused with the wall. That would be a column that is fused with the wall, and that is the wall itself. Now, there exist several approaches to how a shear wall can be designed. Some schools of thought, they take the entire wall section as one element in bending and find the reinforcement for that and distribute it throughout the whole wall. Some standards approach the design of the shear wall as sections. So they have an outer section which is designed to take the bulk of the bending, and then the inner section, a portion of the wall that is near the neutral axis, is provided with minimum reinforcement for walls. So there, if you pick different standards, you find different approaches to how the shear walls are designed. But generally, the shear wall has to be designed for this maximum bending moment that we have calculated, resulting from step number 1 from this loading. The other thing that needs to be designed for is that now we have a wall foundation that is carrying both axial and bending. So this moment has to be designed for in the foundation. For the shear walls. So whenever we are having a shear wall in a building, we will have a foundation that needs to be designed to carry the bending moments resulting from those shear walls. And I'll remind you from your either foundation engineering units or geotechnical engineering units that you have the case of a foundation that carries only axial force from the column, and you have the case of a foundation that carries both axial load and bending, either direct bending from the column or eccentrically loaded foundation that also results in bending. This you were taught in your foundation engineering, and we will mention a little bit of it later on, probably in the next class, because I will talk about columns and how we support them at the foundation in that class. Now that we have said absolutely we have to fix the support of the shear wall at the foundation level. If we do not fix the support of the shear wall at the foundation level, then we do not have a shear wall. This then constitutes the third step of the shear wall design. So we would start with idealizing and loading the shear wall. Then we will use those loads to calculate the bending moments and shear forces. Then we would use those bending moments to design the wall for bending. We have said also that this can either be wind or earthquake, forces loaded at each floor level as point loads on the wall. As point loads on the wall. This is the general approach to how we would idealize, analyze, and design a shear wall. If we were doing this by hand, now, since we are not doing this by hand, I will digress a bit here and say aside. This is how you will do this thing on your building, on the hypothetical building that we are trying to design. We got the building. I did mention yesterday that I will require that we will do the analysis for lateral loads by two approaches. One approach is we will have a file where we will load manually the lateral forces. So this is let's assume this is our building, the whole 18 floors of it. Once we calculate the wind loads, for example, per floor, we will come and load them per frame, sorry. We'll come and load those forces as point loads there in the X and in the Y direction, wind and earthquake. So we will have the building looking something like this with point loads at the nodes. These are the forces that we have calculated per frame, which I saw the group that made a presentation yesterday managed to calculate those forces. Okay, so X and Y directions. You come and just put them as point loads at the nodes because they are loads per frame. So at each level, whatever load per frame that you have calculated, you come and put it in there, in the X and in the Y direction. So you do this for wind and you do this for earthquakes. Up to that point, ladies and gentlemen, any question? Anybody with a question or a thought or a suggestion? Anybody with a question, a thought, or a suggestion? Great. So now I want to pause here. We still have some bit of time. We could have one other group showing us how far they've gone. Remember, we want to see how you've calculated your wind loads. We want to see how you've calculated your earthquake loads, and we want to see how far you've gone with the model. Just as what the first group did yesterday. We can have one group before we get to 9 o'clock. Yes, Sean.
This is our work for group 4. I will present.
Okay.
I'll show the Excel sheet and the model.
Okay. Maybe as you upload, you could tell us who are the members of this, your group 4.
Let me. We have Shalin Njeri.
Shalin.
We have Suleiman Kodo. And John Masharia.
Okay.
Eddie Kabaya. And now myself, Sean Maina.
Okay. You said this is group 4?
Yeah.
All right.
Yeah, so this is our Excel sheet. We have both sheets in the same document. This is our wind loading. So my group and I were trying to also automate these. We are also trying to automate the extrapolation for S2, but we are yet to prepare an Excel sheet. We are still learning how to. But yeah, this one we calculated by hand, all these values. Then these are the ones they were input by now the Excel sheet. We made formulas for them. These are the formulas up here.
Okay.
And now this is our earthquake loading. So from other groups yesterday presentation, there were some disparities in our values. Yeah, I'm trying to find out where we may have gone wrong or where the disparities are coming from. But generally, these are our earthquake forces. This one of the weight per floor. These ones are calculated by the formulas. Yeah. I'm waiting for my Revit to open up. I believe it has.
Okay, just before you remove this one, whatever disparities you are finding does not mean that your work is wrong.
Okay.
It might be also that the other group might be wrong. So I think it's important when you find those, then you sit together and try to find out what is causing the difference, so that then you can zero in on whatever it is, and whoever might have not gotten it right might then be able to rectify.
Okay.
Yes, and this applies to all the groups. And I'm saying that because I'm not bothering to really check the numbers to say this is correct in terms of numbers. I think once you get the concepts, that is good enough. Okay, you can show us your modeling.
Oh, our model. Okay. Unit.
Shibega is asking, how will the shear wall behave to the lateral loads from the other directions? For example, if we design considering the y direction, explain how the wall will behave to the loads from the x direction. Of course, the shear wall that we've put, like in this this example, it's really useless in the x direction. So if you have to provide stiffness for the building in the x direction, you also need shear walls in that direction as well.
So I hope.
Yes, we can see your window.
Model.
Yes.
So I know you never told us to add the foundation. I just
yeah, that's okay. If you put in the foundations, that's perfectly in order.
I just used the one that was available just for making the building a little bit neater. So these are our 3D view. So the software that I myself am using is allowing us to do real-time analysis using its own AI. It's around here for the analyze. It has an Autobot that analyzes your building as you go on, and it develops something that like this. This one. Now this is the analytical model. If I add loads in the physical model, it will come and apply this one as well. It will apply here. So it looks like. Okay. Sorry for the noise. There's a bit of construction around here. Yeah, okay. That's what we've gotten. I don't know. Let me try and show an elevation view. Yeah, these are our elevation view. If I can open one of the floor plans, yeah, it looks like this. This is one of the floor plans for one of the floors. We have this is the slab, and you have a few of the beams and columns here and there. Yeah.
Okay, so you're saying you have run an analysis for this already?
Okay, it doesn't have any load yet. It's just the analysis of the building without any. Okay. Yeah, that's why the.
Tell us. How are you intending to put in the loading? For example, the self weight of the elements of the building. So will this pick it for itself or what?
Okay, so you come here to you can use the analyze one, where you come and put the loads here. This is the tab to add the loads. They give you the different type of. You have to add them manually. I've not yet known how to automate them. Okay,
not a problem. Don't worry too much about it. I think I like the progress of this group as well. Now you have said my group and I when you're starting, and then along the line you said this is the software that I use. I'm just wondering whether the rest of the group also is able to do what you're doing, because the idea of having these groups is everybody has got to be able to fumble their way around. I don't know whether that is correct.
We've been having weekly meetings whereby everyone has to show their progress on their own softwares. And as of yesterday, 3 of the 5 group members had gotten to where I am right now.
Okay. So
Yeah,
how about the other fellows?
The other fellows are still saying that their software is bothering. Bado wanasema that wakijaribu to start it on their PCs, it's failing. So they're still on the...
Simu wakwamue ndio muende pamoja.
Yeah, najaribu kuwakamua by suggesting...
Si kuwakamua.
Kiswahili bwana kidogo nikiga chenga.
Sawa, nitaacha kusema Kiswahili kabisa kwenye class hichi. Kiingereza peke yake.
It's okay.
We will only speak English in this class sessions.
Yeah, so I'm trying to get them unstuck by suggesting other places where they can get those softwares.
Yes,
one of them I'm planning to... Pardon?
This applies to the whole class. It is better when everybody is able to walk in step with the entire group than to have a few people who are way ahead and the rest of the group is basically just left behind and clueless. It's not a good way of learning. The more we have everybody about the same level, the better the discussions. You see, we have what, maybe an hour 15 minutes to sit in class like this to discuss. But you guys, in your own time, you arrange, you meet, you discuss. When you're chatting, just even on the corridor, you can throw ideas like, you see this feature here, what. So when everybody in the group is in step, then it makes the discussions a lot richer than when others are behind. So I urge for the entire class, ensure that you are in step and don't accept to leave others behind unless they're difficult people, because I'm also aware that there are people who are just difficult. They will not cooperate and they will not want to be part of the process. Those ones you can leave behind, but as much as possible, try and walk in step with others. Okay, so I'm happy with the progress of this group. Keep going. I think you can make an attempt to put in, now this is for the whole class, you can make an attempt to put in both gravity and lateral loads. And as we said at the beginning, there's a lot of tutorials. I really cannot teach you, like this software these guys are using, Revit. I've never used Revit, so I really wouldn't know what is where. But it's them who are using, so they would know how to find whatever information they need, tutorials. The beauty is that now with the YouTube and places like that, is a lot of tutorials for how to do this or how to solve this problem. So that's a good thing, and please take full advantage of that. So thank you, Sean and your group. Maybe we could have another group if they can upload quickly.
Yeah, let me share ours, group 5.
Okay. So Mutero, please, you can go ahead. You're saying yours is group
5.
Group 5.
Yes.
This gentleman is asking, how do you determine the location of the shear walls in a particular structure? Okay, so I'll talk about that in the next session. And
please confirm that you can see my screen.
I can see. Please just hold a bit. I respond to this gentleman. He's asking. I think he's asking a good question. This is Nixon. So I will talk about that in the next session. And my desire was that by the time we get to that point where we say what size of shear wall and where do we put it, if you could have the models ready and maybe even loaded with these lateral loads, so that when we discuss in class, you go and actually put those shear walls and run the analysis and see the implication of having a shear wall at this point or the other one, because there are serious implications of where you place your shear walls and the size of the shear wall as well. Okay, so I urge everybody to please push their work as much as possible to have the model, to have the loading put in somehow, so that when we discuss this item that Nixon is asking, then you can actually go and put in the shear walls and run an analysis and see the actual outputs from that analysis. Great. Mutero, I think you can proceed.
Okay. Our members are Sharon, Awino, Muiga Mutero, that's myself, Gilbert Shibega, Morgan Nyakundi, Caleb Mukenya, and Joseph Kuria. Okay, so this is our table for wind loads. We started by putting out, okay, it's a Class C building, and the location is outskirts of Nairobi. And that is what gives us the values for S2 from the code, from the code of practice. And then, so to start us off, S1 and S3 are just 1 and 1 all through. So to obtain this S2, we went to the table in the code of practice, and then now to obtain this dynamic wind pressure, and then we would have, okay, starting with the design speed, we'll have our design speed of 28 multiplied by the S2 and S1 and S3 for each flow to give us these values on this column. For dynamic wind pressure, we also have a formula for that, including K and the design speed squared, and then the total force now for each story is given by the dynamic wind pressure times the area. The area in the y direction is shown here for each flow, and the area in the x direction shown here for each flow. Then the total force per story, as I've explained. Then we have the force on the inner frames, and then the force on the outer frames, because the inner frames are carrying more force than the outer frames, as we had seen in class. So this is for the x, for the y direction, and this is for the x direction. This table here is just to help us interpolate for the values from the table to get S2. For our earthquake, the seismic loading, and then again, Class C in outskirts of Nairobi, zone 7, soft ground. And then we have a bit of formulas for each. The time of vibration formula is shown here, and then we can calculate that for the x and y direction. When you go to the C basic, we also have its formula, and we have calculated for the y and x direction. And then for the site specific, the coefficient, which is 0.65 times the C basic, then we also have it for the y and x direction. And then for the total base shear in the x and y direction, we have them here. So now the table, we have the story number 1 to 18. We have the weight of the building calculated with the total calculated down here. We have the height of the building from first floor to the 18th floor. And then the products of now the height and the weight also totaled up down here. So these totals are the ones that we now use to get to distribute the forces in the x and y direction. For the 18th floor here, the formula is a bit different, because we have 0.04 times F, the force, which is calculated for, this is the y direction, so it is highlighted here, the y direction, multiplied by, according to the formula that was given in the code, to give us the force for the top floor, that is in the y direction and in the x direction. Now, these other calculations for the y direction for each floor, the distribution for each floor, is now based on the other formula that is now taking the total force minus the force for the first floor, and then distributed to all the floors in the x and y direction. Again, as Sean has noticed, our value here for the 18th floor is a bit different from what yesterday's group had, and what we have is similar to what Sean and his group has. So I think they could relook at that. Yeah, this is now our table for seismic loading.
Okay, great. So thank you. I think I like the presentation of this group, both on the table for wind and the table for earthquake. It's a bit easier to follow. a lot of times when you make a good spreadsheet, later on 5-10 years, when you come back and you want to reuse it for something else, it's easier to to put in parameters for different buildings. So I encourage everyone to also try and just have a good format. But generally, my feel at this point is that on these lateral loads, based on the two very old standards that we did, I think you guys have pretty much understood, picked the feel of these two standards. So I'm very pleased with what I'm seeing in terms of these presentations. Now I want to throw a challenge to you. If you find it, if you can find time, pick for example, the Eurocode, because our country is moving to the Eurocode. Pick the Eurocode and see what it says about the wind. If you like, you could do a parallel analysis for wind. Could do a separate spreadsheet for wind to Eurocode. So we have wind to CP3 and wind to Eurocode. Also, then you could also do the same. Pick the Eurocode for earthquake, see what it says, and see if you can propose loading for the earthquake to the Eurocode. If you're able to do that, basically what happens is that you'll learn better. You learn better. You get a stronger grasp of the concepts, and as you graduate and go out, you'll have a good head start on these particular issues. So I can see here, this is your model. Yes, please proceed.
Yeah, this is our model. It's just typically the 8 floors, the 18 floors, sorry. And then for each of the columns that we have, we had to assign a property. So we give the property 800 by 800, the concrete, and then the density of that concrete, the unit weight of that concrete, so that the software can now pick the self weight of the building. But when it comes to the other loading for the wind and the earthquake, we'll do that manually. So I don't think this is different from what the first group showed us yesterday. This is just a model that we have, both in plan and in the 3D.
Okay, so thank you. I am suggesting that you can proceed and put in the loading, both gravity and lateral loads, onto these buildings ahead of our discussion in the coming session. My intention is I will talk briefly about how we support columns, because I don't want to tell you to fix the columns or to pin the columns at the foundation level. I want to put across a series of thoughts for you to make your own decision what you want to do with the support at the foundation. It's better if you know the considerations and the thoughts that govern this decision, then you make a better decision on your own. Also, I have said that the intention is to also discuss a little bit about where we would put the shear walls in the building and what implications those shear walls would have. Again, this one, I think we will, I want us to discuss this in the coming session, so that immediately we do that and you have a model and it has the loads. You put in the shear wall, you analyze, and you see what kind of forces and what kind of behavior the structure has in terms of the position and maybe even the sizes of the shear walls. So we'll discuss this in the coming class. This is helping with your learning, because they learn. We will. Okay, if you learn, then we are all successful, because that's what we want you to do. We want you to learn. So thank you very much. Unless somebody has a burning question, I think we will wind up at that point, and we meet again in the next session. Thank you, and good morning.